Hello, this video is about the preparation of input files for the Climatol package. The Climatol R package contains functions for quality control, filling in missing data, and homogenization of climate series from different weather elements and temporal resolutions. Monthly and daily are the most common. Like the rest of the R packages, it is free, open source, and multi-platform. The version in the current repository can be installed by the usual procedures of the R programming environment. Alternatively, you can download the development version available at the Climatol website, climatol.eu, where you can also find user guides in English, French, and Spanish, as well as a couple of explanatory videos. This is one of them. Let's see the web page, but mierda. So you have here 3 tabs for choosing the language, and also the development version, which I recommend to download because I will be basing this exercise in this version, which adds some more functions to the published version. Also available is the guide in English in this case, but this guide is referring to the published version, although it contains the basis of the software, of the methodology, and also explains some of the results, how to interpret the results and other things. So this video is just a complement to this guide to explain how to prepare the input files. The preparation of the input files needed for this software are just 2 text files, which is first a file varchly, which would be a short name of the climatic variable that you are going to analyze. An underscore separates from the initial year, hyphen, and then the final year. This is the base climate, the base name for the input files for Climatol, and the stations has an extension .est, and this file contains the coordinates x, which will be the longitude in degrees with decimals, y, the latitude in degrees with decimals, z, elevation in meters, codes and names of the stations, and another file with the same base name but extension dat contains the data of the entire period for the first station, followed by those of the second, and so on, in the same order as they appear in the station file, using a dot as decimal separator. Both files are plain text, so Windows user can edit them with Notepad or other similar applications. The data are separated by spaces. An example of the est file would be, for example, here you have the longitude, negative if it's west, latitude would be negative for southern hemisphere, elevation in meters wouldn't need any decimal, but in this case there are some, the code of the station, and then the name of the station. The name of the stations should be quoted to avoid problems when the name contains spaces, because the space is the separator of the fields in this file. And an example for the data file would be just this, can be the first lines of a data file is just the dates, the data. So no reference to the dates, no reference to which station they belong to. They are all the data for the first station, and any missing data must be paired with NA, which is the standard code in R for missing data. If this is short for not available, or you can use any numeric code, like for example -999. So depending on how the observed data are stored, you can write a script in any programming language to read the data and write them in the Climatol format, or you can try using some of the helper functions provided in the development version of the Climatol homogenization functions. So after having downloaded the clihomog.r source file, we would just start our session in R and put this command source clihomog.r quoted. I don't use RStudio. You can use it. You can use the Windows simple but very useful graphical user interface. I just using a plain console text in Linux. So I start R with just capital R and I'm in. So I load the development versions of the Climatol homogenization functions, and they are already available to be used. So now we can use the following functions. We have db2dat that would get the data directly from a database accessible via the ODBC protocol, which must be installed and configured in the client machine, and the R package RODBC. The descriptions of its parameter can be seen in the source code of the function. Example: to extract the daily series of relative humidity with a minimum of 10 years of data in the period 1961 to 2015 in a database that could be called Clima, accessible via user and password pass, we would do assigning the correct names in the database tables and data variables, that giving all parameters in the correct order. It's not necessary to name them when calling the function. So we would start by calling the library RODBC. I'm not going to reproduce this because I don't have usable database here, but we would call the library. Then we would open a connection to the we can call it ch, as in this example, or the name that you prefer. The function is ODBC connect, and then we would begin by giving the name of the database, the user ID, in this case, in this example, user, the password, that could be pass or whatever, and then we would have this ch, or the name that you prefer, is an open connection to the database. So db2dat, we would use the name, a short name for the variable, its relative humidity, we can call it hrel or whatever, the first year of the period we want to study, the second year, number of years with data to select the series. Then we say true if it's daily data, if not it would be false for monthly. We put then the name of the connection to the database, and then we must provide the names of the tables and the names of the variables in the tables. In this case, the data could be in a table called rel humidity. The codes of the stations could be in that table, could be named station. The dates could be date, and the values for the relative humidity could be value. And then the name of the stations table. Let's imagine that it's called stations, and in this table stations, the code of the station could be the same as in the other table, station, and then the name of the station could be name, and longitude in degrees with decimals could be longitude, latitude, and elevation in meters. So issuing this command, he would access the relative humidity for these years. He would select the series with at least 10 years of data and would prepare both files for ready to be homogenized with Climatol. If you don't need the connection anymore, it's good to close it. So, if it's not possible to obtain these files directly as shown above, databases usually implement mechanisms to obtain the series in CSV format, and then you can possibly apply one of the following functions. We have dailyto Climatol that is used to extract data from individual files, one per station, and a stations file. We can look at the description in the source code of the function. I have it open here. This is the source code of cliomog.r. This is the definition of the function dailyto Climatol, and the explanation are in the comments here, with the station, the name of the station file with the names and station coordinates, etc. Parameters, you can read it more carefully, and we are going to see an example. For this example, I will use just a few data files. I can put this in a dedicated directory, which I call data_txt, and we have here, I will remove this from a previous example, and we have here 5 data stations and the stations file. The data, in this case, the names of the stations begin by the code, and they are only the code and then extension txt, and they have this structure. They have year, month, day, precipitation, maximum temperature, minimum temperature from 1961 to 2021. So, and the stations file, which has first the name of the data files. In this case is just the code and .txt, and then you put the code of the station, that is, in this case, it could be extracted from the name of the file, but the name of the file can be any name. So you would put here the code of the station, then the station name, latitude, degrees with decimals, longitude, degrees with decimals, elevation with in meters. In this case, there is also the country. These are Chilean stations from the north of the country, but you wouldn't need this. Then we can set the working directory to data.txt. We can check if we are in the correct directory, and yes, we see here the files with the data and the file with the stations. So the command we are going to issue is dailyto Climatol. We give the name of the stations file, which is estaciones.txt, and then we put the columns that contains first the name of the files. They are in the first column, then the data as they are needed in the file, the stations file for Climatol. That will be first the longitude. The longitude is in the 5th column, so we put the 5 here. Then latitude is the 4th column, 4. Then the code, the elevation, which is in the 6th column. Then the code of the station, which is the 2nd column here, and then the name of the station, which is the 3rd column in this file. And then we would say that in each of these data files, in which columns are year, month, day, and the data we want. Let's imagine that we want to extract the minimum temperature. Minimum temperature, we saw that it's in the 6th column. So we can put, we can call the variable tmin. Oh, sorry, we are here. Year, month, and day are the first 3 columns, and then in the 6th column is the minimum temperature. So these are necessary data for the function to extract the values of the variable that we want. And now we say the acronym of the variable, we can say, we can call it tmin, and I'm going to extract only 10 years from these variables in the data files from 2011 to 2020. I'm going to ask for a minimum of, in this case is not years, it's data as they are daily data. I will ask for 5 years of data, which are 1825 days. The separator is white space, so it can be explained, it can be set as an empty string, character string, and I have seen that the missing data code in this case is -99.9. So I specified here with the variable na.strings equal -99.9 quoted. Then I'm going to issue this command, and the function is reading the 5 data files, and then it provides a statistical summary of the data that it has read. In this case, it says that it informs you that data have been saved in this file, tmin_2011-2020 .dat, and this is the statistical summary of the data. If you see something strange in the data, the reason would be that there has been some incorrect specification of the columns in the data, or another problem. It gives you also the number of missing data in the file. And also from the stations file, it informs you about the station coordinates and names saved to file tmin 2011-2020 est. These are the longitudes, the statistical summary for longitudes, for latitudes, for elevations, and well, there's the code names. It gives you also, in this case, a statistical summary because codes are numeric. If they were alphanumeric, it wouldn't say, it wouldn't issue a statistical summary, of course. And that's all. So we would have, these are the est file for Climatol, and these are the data files for Climatol. However, many users have their data in individual Excel files, one per station. Then the first step is to read these files and save their data into a unique CSV file with the function xlstocsv that requires the installation of the readxl library. The Excel files can contain data for several variables in different columns for a single station, and their names must start with the code of the station followed by a separator, by default an underscore, but you can specify another. Examples would be 0323 underscore Alamillos XLSX. In this case, the name begins by the code of the station, and then it has the name of the station. You can put here any other details of the file. Another example is just the code of the station and .xls, and nothing more is needed. These files must contain at least one header line. If they contain more, supplementary header lines should have at least an empty cell in the columns of date and data to be read. The description of the parameters are also in the source code of the function. To see the parameters, we will look in the source file. I will look for xls. Okay, this is the function, and directory is a temporal directory where the Excel files will be placed to be processed. After processing them, they will be moved to an archive directory. Then we put the an acronym for the variable that we are going to extract from the Excel files. We will say which extension they have. By default is xlsx, but it could be xls, and also in which are the data columns that have year, month, day, and the value of the variable that we want to extract. Also, if the code separating the character separating the code from the rest of the name is not an underscore, we should specify it. So let's see an example of how this works. Here I have placed a few Excel files in a directory that data underscore xls. So I have called, you can choose the names of the directory that you want. This will be the initial directory where the Excel files will be placed. I have 5 Excel files. Here they don't have a numeric code, they have 3 capital letters as a code, and they are separated from the name of the files, of the stations, by a hyphen instead of an underscore. So we will have to specify this character separating the code from the rest of the name. Let's see one of these Excel files. They have a very simple structure. They have a header line and then the data. They have also, like in the previous text files that we processed before, they have precipitation, maximum and minimum temperatures. In this case, I will prepare data for homogenizing the precipitation. So the columns are 1 for the first for the year, second for the month, third for the day, and the fourth column is the one containing the precipitation data. Then, so we must move to the directory we were here. We will move to the directory containing these 2 directories. Oh, an error here, double parentheses. Let's check, and yes, we have the 2 directories. The second directory is empty, and these files, after being processed, will be moved to the following directory. In this way, you can, if some of these files had an error or something and was not processed, you can fix it and run the function again without the need to process all the files again, only the ones that you didn't success to process. You can also add new files, and the destination file will all data will be accumulated, will be appended to the file. So if you want to repeat the process from the beginning, you should delete the file that will be accumulating all the data of this variable in all Excel files. So once we are here, we call the library readxl, and now we can proceed. We will just, as in the data columns by default are 1 to 4 and precipitation is in the 4th column, we don't need to specify this. If we wanted to extract maximum temperature or minimum temperature, we would have to say that columns equal C 1 to 3 and then 5 or 6, but in this case the default values are okay for us. So we apply this function in this way: first directory where the Excel files are, and then the archive where they will be moved. Abbreviation for the variable we are going to process, and the code separation, the character separating the code from the rest of the name. So it has read these 5 Excel files, and it says that the data from these 5 xlsx files have been saved into the all-preg data CSV. This is the short name we apply for the variable. Station codes lists have been saved into all-preg stations.csv, and it informs you that the original files have been moved to the dir2 directory. In dir1 there isn't any file anymore, they have moved here, and we have these 2 new files. All-preg data has all the data, first for the BRU station, and it's a long file. It has the code, year, month, day, and the value. By the end of the file, we see that we have the data of another station. And then we have just a list of the stations, just the codes. So we now have all the Excel files, all the data that we wanted has been read and has been placed in this all-preg data CSV. Now we must convert this data to input data files for Climatol using another help function, which is CSV to Climatol. For this we need the name containing the data, in this case all-preg data CSV, the columns that contain the codes and the other 4 elements, year, month, day, and the data. And we also need a stations file, and we will say in which columns are the codes and the coordinates, etc. We use the acronym of the climate variable. We specify also minimum number of data items that we want to have in our series. In this case is also just a minimum of 5 years, 1825 data items, which corresponds to the dates of these 5 years without counting the leap years. So I had prepared these stations, estaciones in this case, .csv, which has the data are the same that are needed for Climatol, but this is a CSV file, has a header, and the data are separated by commas. Then we can use this CSV to Climatol. We could also see the description of the parameters in the source file, and let's imagine that I don't know if there are a special code for missing data, so I just run this function in this way, and then has creating preg input files for Climatol from all preg data CSV, and this is the list of codes that he has processed. There is also, like in the first example, a statistical summary of the data, and yes, we see here that the minimum value, and these are precipitation data, minimum value is minus 99.9, so we can deduce that this is a code for missing data. Then what we do is to repeat this command and to specify that the not available strings are minus 99.9 between quotes, quoted. The process is repeated, and then we have now the data in Climatol format. Let's update the contents of the directory, and here we have preg underscore 1980 to 2019 D80 and preg 1980 the stations file. Data, as always, and the stations. Well, that would be all. An important note is that relative homogenization benefits from a high density of stations. To increase it, do not hesitate to use short series. With just 10 years of observation, they are already very profitable as long as they have an acceptable quality. Here for this example, I have accepted even a minimum of 5 years of data. Climatol requires that no time step be completely void of data in all stations, because in that case it would not have any reference to fill in the missing data. If no other series can be added to provide data in those critical periods, one or more series from some reanalysis providing daily data of the static variable, NCEP, 20CR, ERA5, etc. can be used. If we are going to homogenize a series isolated, which is far from any other with which it might be correlated, the use of a series of reanalysis is the only resource. For this, it will suffice to append the reanalysis series to the end of the DAT file, and also align with the coordinates of the grid point and the dummy code and name at the end of the stations file. The code in this case for the reanalysis series must start with an asterisk, and if we are homogenizing a single series, we must add the parameter force true to the homogen function, because otherwise, if it finds a discrepancy between the reference and the problem station, but there is only one reference, he wouldn't do nothing, he wouldn't do anything, because there would be the uncertainty or to which of the two series would be the problem. But in this case, as we trust the reanalysis series, putting force equal true, we would homogenize and infill the data and remove any big outlier, even if only the reanalysis series is available. But on the contrary, we could be in the place of homogenizing the series of a very large area with a variety of climates. Then it would be necessary to subdivide the territory into smaller zones with a more homogeneous climate. And that's all for this first video, which was devoted to the how to prepare the input files. The problem can be that any user probably users have the input files in very other different formats. For example, Excel files could be complicated. They could have many header lines with the names of the station, metadata, etc. And that could be a problem to apply this function. But well, it's not possible to prepare a uniform way of producing these input files, because there is a great variety of possibilities of having the original data. So I hope this has been useful, and that's all. In the second video I will explain how to homogenize the series and to look at the results. Thank you.